everyone. Today I will be going over my solutions for the Math Kangaroo 2020 level 9 through 10. My solutions are only one of the many solutions possible to solve these problems, and there are likely some solutions that may be faster or easier than the ones I have given here. First, we will go over problem 1. All of the problems for the first 10 problems will be worth 3 points each. For this problem, we can just count the perimeter of the shape. So the scanned shape was a little bit unclear, so I made another model of it. And then here we can just label each of these segments, which are given to be 1 centimeter. We can just label each of these segments as 1. So then we continue on. And then you could either just add all of the ones together, or you could first group them into each side. So these two ones correspond to this side, which corresponds to this 2. These two ones correspond to this side, which corresponds to this 2. And then you could just add those up if you want, and then you could get 18. Next we have problem 2. For this problem, we can immediately notice that A is 4 digits, because it's a 4-digit number plus a 1-digit number. And then you can just see it will easily just be 2,000 something. B is 3 digits, C will be 3 digits, D will be 4 digits, and E will be 5 digits. So obviously E is going to be the largest number because 5-digit numbers will always be larger than 4 or 3-digit numbers. And B and C are going to be the two smallest numbers because they are 3-digit numbers. Thus, the middle number, which will be the third largest or the third smallest, will be the smaller of A or D. So if we were to, for example, to order it out, we know that for the first smallest and then the second smallest, we have B or C. For the largest, so we could just say fifth smallest, we have E. So that only leaves the third and fourth places, which will be occupied by A or D. And for the middle one, we want to figure out which one the third is. So we need to figure out, is A smaller or is D smaller? Because the larger of them will be on spot 4. So to figure them out, we can just add the expressions together. A evaluates to 2,346, D evaluates to 1,239. D is smaller, so it will be the third smallest, so the answer will be D. And alternatively, you could just evaluate all the expressions to their exact number and then compare those numbers instead of looking at the digits. Just whatever works for you is fine. Next we have problem 3. So first we consider that Anne's mother's mother is Anne's grandmother. The mother of Anne's grandmother's daughter is just Anne's grandmother herself. So that would be E. So just to draw it out again to make sure it's clear, if we have Anne here, so then her mother's mother, so I'll just say M for mother. Well, her mother's mother will be her grandmother, I'll just say GM. Her grandmother's daughter will be, so let's just say I'll label this as step 1. So mother, step 1, mother's mother, step 2. The daughter of her, step 3. So when you look at the daughter of Anne's mother's mother, or Anne's grandmother, it'll just be Anne's mother. And then step 4 is who's the mother of that daughter? Well, then we go back to Anne's grandmother for step 4. So it's just Anne's grandmother, which would in this case be E. So now we have question 4. For this question, it's actually quite tricky. It initially appears that there are 6 closed rings. So it looks like there's one closed ring here, one closed ring here, one closed ring here, and then just back down the rest of the shirt. However, it is important to consider the back of the shirt when determining whether a ring is closed or not. So that sounds kind of confusing and it sounds difficult to visualize. But if the shirt were transparent, but you could still see the stripes, the pattern will look like a spiral that does not close, like this pattern on the right. So therefore, there are 0 closed rings, which would be A. So once again, if I were to draw a comparison, so this shirt, it would look like a bunch of closed rings, right? Because it also goes on the back. The stripes continue on the back to form closed rings. However, when you stagger them, this ring, the stripe on the back, will end up leading into the next ring. So there's a stripe on the back of the shirt, right? But ends up leading into the next ring, which will end up leading to the ring after that. It'll just keep on going in a loop. While over here, if you go to the stripe on the back, it'll just go back into the same ring and it'll close itself off. And once again, it closes itself off. For problem 5, we have the number AB, in this case, each representing a digit. So for example, if we had A is equal to 1 and B equals to 2, we would have the number 12. Well, this 12 is equal to 10A plus B, or in this case, it'd be 10 at A, which would be 10 times 1, plus B, which is 2, and that's obviously 12. And we can have CD equal to 10C plus D. So make sure you know that in this case, when we write like this, AB, it means each one acts as a digit, like the 1, 2, and 12. While when you write it like this, we have each one acting like a variable. So it would be 10 times A plus B. Well, here it's not A times B. So moving on, we see from this equation here that 10A plus B plus 10C plus D is equal to 79. Because this equation is telling us that AB plus CD is equal to 79, and we can just substitute in what we have written here into that equation. So using this method to convert this expression on the right, which would be this expression here, so converting, and this method refers to writing it out using 10A plus B or 10C plus D. So using this method, we get 10A plus D plus 10C plus D plus 10A plus B plus 10C plus B. So remember, for each of the tens digits, we just add a 10 in front, and then for the ones digit, we just added them. So we have this expression. Now we can group the expressions together. We see here we have 2 10A's and 2 B's. So 2 times 10A plus B. We also have 2 D's and 2 C's. Sorry, 2 10C's. We can also group those together to get 2 times 10C plus D. And then we can group all of these together to get 2 times 10A plus B plus 10C plus D. Substituting in this equation here for this one, we get 2 times 79, which is equal to 158, and that is B, our final answer. For 6, we let x be the smallest integer in the sequence of 4 consecutive integers. Then the sequence would be x, x plus 1, x plus 2, and x plus 3. The sum of this sequence is 4x plus 6. Thus, we can create an equation 4x plus 6 equals 2. Because remember, the sum of these 4 consecutive integers is 2. And then 4x plus 6 represents the sum, where x is the smallest of the integers. So subtracting 6 from both sides, we get the equation 4x equals negative 4. And finally, x is equal to negative 1 for C. Of course, we should make sure that x equals -1 does actually work. So we plug it back in. We check, we have the series -1, 0, 1, 2. And if we add it together, it does indeed equal 2. Alternatively, you could try to just guess the sequence directly. Since the numbers are pretty small, it's relatively easy compared to having a larger number like 100 or 200. So we can just think, oh, the sequence must be somewhere around 1, 2, 3, or 0, 1, 2, or maybe even -1, 0, 1, 2. And then from there we can yield our answer, this sequence right here. So we need -1, the smallest of that sequence. For question 7, we first need to make sure that we understand what the question is asking for. So the years consist of a 2-digit number repeated twice. So we have 2020, 1717. So we need to find the next year that has this property. So first we notice that years in such a fashion, they're just a 2-digit number repeated. So we just have 17 repeated twice, 20 repeated twice. If we had the 2-digit number 18, we could have 18 repeated twice. So each time, the next smallest number for which this property holds true would just be the next 2-digit number. So the smallest one would be, say, 1010. And then if we want to get bigger than that, we just, instead of using 10, we use 11 to get 1111. So from here, we realize that we want to find the smallest 2-digit number greater than 20, which is 21. So the next year with the stated property is thus 2021, which is 101 years after 2020. So the answer is B. For question 8, we first need to realize that cutting 3 squares creates 6 triangles. So at least 6 of the 13 pieces, and these 13 pieces are the pieces that she now has after cutting the squares. So at least 6 of these pieces must be triangles. And since each triangle has 3 vertices, there will be 18 vertices. There are still 24 vertices spread within the remaining shapes, because remember that there are 42 total vertices. So 42 minus 18 is 24. There are still 7 remaining shapes. From here we can create a system of equations with s equal to the number of squares and t equal to the number of triangles. So each square has 4 vertices, each triangle has 3 vertices. So 4 times the number of squares plus 3 times the number of triangles must be equal to 24, the total number of vertices, within the 7 remaining shapes. And then the number of squares plus triangles must be equal to the total number of shapes, which is 7. So solving the system of equations, we get s equals to 3 and t equal to 4. And then, so if we were to actually solve this equation, without knowing the answer, we could use elimination. So we could multiply the bottom equation by 3, both sides of the bottom equation, and then we could eliminate this. So we could get s equals to 3, and then t equal to 4. So after we get this, we see that there were 4 triangles originally, and the answer is 4. And the reason why we know that there are 4 triangles originally is that we have to remember to ignore these 6 triangles that are newly created, because originally those triangles were squares. So these 7 shapes were all originally the same shapes because they were not altered in any way, but these 6 triangles were originally 3 squares. So if we were worried about all of the original shapes, we would have 4 original triangles and 6 original squares. We have to remember that these 6 modified triangles used to be squares, 3 squares. So now we are moving on to the 4-point section. First we have problem 11. For this problem, we can first realize that we only need to consider the first 4 of the 18 days. Because no matter what day the next 14 days start on, they will always be exactly 2 weeks and contain the same number of story days. And then they'll just, so 2 weeks, it'll always just contain 2 of each day. So we don't need to worry about those 2 weeks because no matter how they start, they'll always contain the same number of days. They'll contain the same number of, they'll always contain 2 Mondays, 2 Tuesdays, 2 Wednesdays, only up to 2 Sundays. And that means that no matter what, they'll contain the same number of story days. So writing out the days as story and non-story, we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And then Sunday's story, Monday's non-story, story, non-story, 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 story. So just to be clear, these the ones on the same vertical are corresponding days. So what we need to figure out is when should she start her trip so that the first 4 days contain as many story days as possible. In this case, the 4-day period which incorporates the most story days starts on Saturday, so this would be day 1, and then goes through Tuesday, so day 2, day 3, day 4. So the answer would be Saturday D. And then if you want to double check yourself to make sure that the next 14 days really don't matter, you could just write them out and then for yourself and see that if you start on Sunday, it'll still contain it'll contain the same number of story days as if you start on Monday, Tuesday, Wednesday, or any other day. So now we have problem 12. So first, we substitute the equation they give us into this expression. So we find that ABCD is equal to 2 times CD, which is we got by substituting 2CD for AB. So multiplying that out, we get 2 times C squared times D squared. So because A, B, C, and D are integers, ABCD must equal twice a perfect square. And then just to make sure everyone knows why, we have 2 here, which is where the twice comes from, and then we have C squared D squared, which is a perfect square because that's also just equal to CD squared. So going through the answer list, the only number which is not twice a perfect square is 100, because 50 is not a perfect square. If you want to just make sure for the rest of them, this is 25, which is 5 squared. This is 50, which is not a perfect square of anything. It's actually 5 square root 2 squared. For this is 100, which is 10 squared. This is 225, which is 15 squared. And this is 400, which is 20 squared. So the only number which does not satisfy our condition which we found here, which is ABCD must equal twice a perfect square, is B. Now we're on question 13. So I personally think that the wording of this problem is a little confusing. I'll be operating off this, for the rest of the solution, I'll be operating off the assumption consistent with the answer key, where the first signpost is on our left and the second signpost is on our right. So in this case, what it would mean is that, let's just say the path is walking straight down here. This signpost is the way you would see it as on the path, and this signpost, the second signpost, is the way you would see it on the path, as if the path were right here. So, just to be clear, in this case, this sign would be pointing backwards. This sign will also be pointing backwards. This sign will be pointing forwards, while this sign will be pointing backwards. So I'll actually write it using this way. So both of these signs will be pointing backwards, which I'll represent using a down arrow. This sign will be pointing forwards towards the path, which goes this way, which I'll be representing with an up arrow, while this sign is pointing backwards. and then these two signs are pointing forwards, or towards the direction in which you're traveling on the path. So this means that in between the two signposts, we travel 3 kilometers further away from A town and 3 kilometers closer to C town. Because you see, we travel 3 kilometers forward, so the distance between us and C town decreases by 3 kilometers. And we travel 3 kilometers on the path, so the distance between A town increases by 6 kilometers. Thus, it means that we have already passed through B town because it takes 1 kilometer to get to B town, and then we have traveled an additional 2 kilometers away from B town. So B town is now 2 kilometers behind us. So the number written on the sign is 2. And that answer is B. Next we have question 14. So we have a triangle with side lengths 20, x, and 2/5 x. And then we just have x equal to one of the other side lengths, and then 2/5 x is because it tells us the side length is equal to 2/5 of the other one. So because the triangle is isosceles and x cannot equal 2/5 x, since triangles cannot have side lengths of 0, 20 must be equal to either x or 2/5 x. So if 20 is equal to x, we get 2/5 x is equal to 8, and we get the sides 20, 8, 20, and perimeter 48. If 20 equals 2/5 x, we get x equals 50. However, a triangle with side lengths 20, 20, and 50 does not exist because these side lengths do not satisfy the triangle inequality theorem, which is the sum of any two sides, in this case A and B, must be greater than the third side, C. So for here, the sum of the sides 20, 20 does not exceed 50. Thus, this solution is extraneous, so we can just cross it out, and we only need to worry about this perimeter, which is 48. Now we have problem 15. So there are many ways to fill in the numbers in the circumference, but we only need to find the one where all pairs of opposite numbers have the same sum. So since the question tells us that he wants to be the sum of the 3 numbers on each diameter be equal to 13, then the sum of these 3 numbers must be equal to the sum of these 3 numbers, which must be equal to the sum of these 3 numbers, and so on. So since this number will always be the same, since you're just adding it multiple times, but it doesn't change, we have to realize that this number plus this number must be equal to this number plus this number, which is also equal to this number plus this number, and so on and so forth, in order for the numbers on each diameter to be the same sum. So the easiest such configuration is where all numbers are 5. Because remember, there are 8 numbers on the circumference. Their sum must be 40. So if each of these are 5, then any 2 numbers will obviously equal any other 2 numbers added together. And then 8 of the 5s will equal to 40. So thus, 5 plus 5 plus x is equal to 13, where x is the center number. Because remember, he wants the sum of the 3 numbers on each diameter to be 13. So we have 5 plus x plus 5 is equal to 13. From this equation, we get x is equal to 3, which is A. Now we have problem 16. So doing the same thing as Masha did for all numbers between 2010 and 2099, we'll create 20 times x, where x is between 10 and 99. Because essentially what you're doing is you have 20 times, so let's say you have 12, right? You're just putting multiplication sign here, and then we have equal 20 times x. In this case, x is equal to 12. And then we have all x between 10 and 99. because the first two digits will always be 20, because it limits it here between 2010 and 2099. So for a number to be a square, the exponents of its prime factorization must be even. So for example, for the number 20 times 20, its prime factorization is 2 to the 4th times 5 squared, and the exponents will be 4 and 2. These exponents are even, so the number is indeed a perfect square. For another example, let's say we have the number 36. Its prime factorization is 6 times 6, which is equal to 3 times 2 times 3 times 2. And then we finally condense it to 2 squared times 3 squared, which has even exponents. So in this case, the prime factorization of 20 is 2 squared times 5. Thus, x must equal 5 times a square number in order to make it so that 20 times x is a perfect square. Because having 5 turns the exponent from 5(1) to 5(2), which will make it squared. So the values of x that satisfy this property are 5 times 4, 5 times 9, and 5 times 16. 5 times 1 is out of bounds because x is limited between 10 and 99, and this would be 5. And 5 times larger squares are also outside the bounds, because 5 times 25, which is the next square after 16, would be greater than 99. So thus there are 3 such numbers. We have 20, 45, and 80. So the answer is C. So now we are on problem 17. So first, one of the ways you could do it is you could essentially, as shown in this diagram here, you could just look at this shape right here, which is a pentagon. So the sum of the interior angles of a polygon is given by 180 times n minus 2, where n is the number of sides. Thus, the sum of the interior angles of all pentagons is 540 degrees. And then this is also true for our pentagon here, even when it's a concave pentagon. So since the triangle is equilateral, we know that the top angle is 60 degrees, which has already been labeled up here. Knowing that the squares have right angles, we can find two of the remaining angles to be 270 degrees and 90 degrees. Because we know that this is 90 degrees, and so this plus the 90 degrees must be equal to 360 degrees, so that's 270. This angle plus this 90 degrees must be equal to 180 degrees, so that's also 90 degrees. So we have the 4 angles that we know plus the unknown angle, which the question is asking for, must be equal to 540. So the unknown angle is 50 degrees, E. Next we have problem 18. So first we find that the number of kilometers he still must travel is 520 minus 55. He's already driven 55, and he has a 520 kilometer car trip. And the liters of gas left in his car is 14 liters, given here, minus 55 kilometers divided by 1 liter per 10 kilometer, which would be 55 divided by 10. So that means that he has 8.5 liters left, because he used up 55 over 10 liters. With the amount of gas he has, Luca can travel 85 kilometers before refilling. This rules out the 95 kilometer gas station because he won't have enough gas to get there. Logically, he should try to go as far as he can before he needs to refill. So that would be the 75 kilometer distance station. So to make sure that this works, once he travels an additional 75 kilometers to reach the station, he will still have 390 kilometers left to travel. You will have a full tank with 40 liters that can travel 40 times 10 equals 400 kilometers, meaning that he will have enough gas for the rest of the trip if he stops at the 75-kilometer station, confirming our answer D. Next we have problem 19. So first notice that we can divide this first equation, this one on the left, by 17 on both sides. This yields x plus 3y equals 6. From here, we have two options which both lead to the correct solution. For option 1, we notice that multiplying both sides by 9 yields 9x plus 27y, which is equal to 54, which provides the value of 9x plus 27y to be A. Second method is we move the 3y to the other side to get x equals 6 minus 3y. Then we substitute for x in the second expression to get 9x plus 27y is equal to 9 times 6 minus 3y, which is what we substituted in, plus 27y, which is equal to this if we distribute the 9, which is equal to 54a. Now we are on problem 20. So for this problem, it seems complicated at first, but really a lot of this information is extraneous that you don't need to worry about. A lot of information provided in the diagram. So the area of this triangle, each triangle, is 81 over 6 because they're all equal. That's 27 over 2. Because the window is a square, each side must be 9. Select the combination of triangles A and B as labeled in the diagram. We call it triangle C. So this triangle as shown will just be the triangle with these this red border. So it will have area 27 over 2 plus 27 over 2, because remember A will have area 27 over 2 and B will also have that area. So it will have area 27 with base 9, because its base is just part of the square. The length the question is asking for is the height of this triangle. So it's the height because so that is the height because we have this point here, which is what the question is asking for. And it's asking for how far above the bottom of the window. This is the bottom of the window. So then this height, let's just call it h, will just be what the question is asking for. So to find this height, we can just use the area formula for a triangle. 27, which is this triangle's area, is equal to 1/2 base, which is 9, times h, the height. And then we have height is equal to 6, which would be d. Now we are on to the section with all problems worth 5 points each. So we have problem 21. So first, we need to know the divisibility rules. For a number to be divisible by 18, it must be divisible by both 2 and 9. For a number to be divisible by 2, its last digit must be 0 or a multiple of 2. There are 4 such digits out of digits 1 through 9, giving it a 4/9 probability. For a number to be divisible by 9, the sum of its digits must be divisible by 9. So what the problem asking says is that all of the numbers will be created will be using the digits 1 through 9, so that the sum of those digits, 1 plus 2 plus 3 all the way up to 9, is 45. And 45 is divisible by 9. So no matter how the digits are ordered to create a number, the sum of the digits will always stay the same. So thus, all numbers created by randomly arranging the digits 1 through 9 will always be divisible by 9. Thus, the final probability is 4/9, which is the chance that it's divisible by 2, and 1, the chance that it is divisible by 9, giving the probability 4/9, B. Next we have question 22. So first we draw a diagram for the situation. So let D represent the distance the turtle goes before the hare turns, and 5D represents the distance the hare runs before it turns. Because remember that the hare is 5 times faster, and then we know that this length is 5, because it says it's a 5-kilometer race. So we know that is a right angle. It says perpendicular. And then once he realized it, he turned and ran straight towards the point. So, and also x is the distance between the hare's turning point and the finish point. And then this is what we're looking for, x. So using the Pythagorean Theorem, 5 squared, which we can have be a, 25d squared, b, so a squared plus b squared, must be equal to c squared, which is x. So since the hare runs 5 times as fast as the tortoise, we also know that since the hare and the tortoise arrive at the finish line at the same time, that's 10 minus d. Sorry, this should not be 10 minus d. This should be 5 minus d. But we must realize that 5 minus d times 5 must be equal to x, because the hare 5 minus d is the amount that the tortoise travels from the point at which the hare turns, after the hare turns around, and x is the amount that the hare travels after the hare turns around. Since they reach the finish line at the same time, they have the same amount of time to travel, which means that the hare travels 5 times the distance. So substituting this in for x, we get 25 times 5 minus d squared, which is, 5 squared, which is 25, times 5 minus d squared, which is this, is equal to 25d squared plus 25. We distribute the 25. And then we move the terms around to get 600 equals 250d, and then we get d equal to 12 over 5. Substituting back in for x is equal to 5 times 5 minus 12 over 5, which is equal to 5 times 13 over 5, which is equal to 13, c. So now we're on question 23. We can go through the process of elimination for all the options. A is not necessarily true. Although fact 2 tells us that all blue figures are triangles, it does not exclude triangles from being red, meaning that not all red figures can be squares, because there may exist red triangles. B is not necessarily true. Although fact 1 tells us that all large figures are squares, it does not mean that all squares are small, so it is possible to have a small square. C is not necessarily true. Nothing is given about small figures. They could be rectangles or triangles, blue or red. D is not necessarily true for the same reasons as A. Triangles are not excluded from being red. And so that means that there may or may not be red triangles. E is true. Fact 2 tells us that all blue figures must be triangles. 1 tells us that all large figures are squares. So from what fact 1 tells us, we know that all triangles must be small. Because if they were large, that means that not all large figures are squares. So there exists no large triangles, meaning that there are only small triangles. Connecting the two facts, we get that all blue figures are triangles and small, meaning that all blue figures are small, making E the only necessarily true fact. Now we're on to 24. So first, we create and label a diagram. Notice that the shaded shape is a rhombus. You must find the base B of the rhombus. And then if you just want to make sure it's a rhombus, if you were to say rotate this diagram a little bit, then you would have these rectangles. And then quite obviously these rectangles, the shape would be symmetrical. I didn't really draw it well, but just imagine rotating this shape so that it's perfect, so that this diagonal is parallel to the ground. Then there would be two lines of symmetry, this line of symmetry along this line and along this vertical line. So that means that the figure is symmetrical, and all of these sides will be equal. So we must find the base B of the rhombus. You could also call it the side length B, or side length S. It doesn't matter. Whatever variable works for you. So using Pythagorean, you just remember rectangles have right angles. We get 9 plus 9 minus b squared is equal to b squared. And then we expand. We move terms. And then we solve for b. So now we find b equal to 5. The easiest way to find the area of the rhombus from knowing b is to use base times height. So in this case, height would be the line drawn down here. It's the same as the height of the rectangles, which is just 3. So thus the area is 5 times 3, which is equal to 15 centimeters squared. Now we are on to 25. So we must first determine whether the faces used, like the faces given for these 4 sums, include the square face. Because the square face has 4 vertices, while the triangle faces have only 3 vertices each. Each vertex will be used for the sum of 3 faces. So for example, this vertex will be used for this triangle, and then the square. While the the top vertex, which will be this vertex, will be used for 4 faces. All 4 of the triangle faces will have that top vertex. So first, we consider the ways to get each sum using 3 or 4 numbers from this list, 1, 2, 3, 4, 5. So to get the sum of 7, there's only one way, 1 plus 2 plus 4. To get the sum of 8, there are 2 ways listed. 9, 2 ways listed. 10, there are 3 ways. Notably, one of the 3 ways is this way right here, with 4 numbers. If the way that was used to reach 10 was actually this way, then it means that 10 would be the square face, because it has 4 vertices. So 10 is the only possibility for a square face. However, since all the vertices of a square face are used in 3 faces total, including the square face, so it would be only used in 2 other faces, it cannot be the square face. Since either 1 or 4 would always be used 4 times in total. So for example, if you were to choose this one, you see you have 1 and 4. No matter which one you choose here, you would have 1 or 4, and once again, 1 or 4. 1, 4, and there's one way to choose it without 4 of 1 or 4, but that would create 4 2s. And there's no vertex which can be used in the square face, which is used in 4 faces total, because the only vertex used in 4 faces is this top one. So no matter which combination of if this 10 is the sum of the vertices of a square face, there's no combination of numbers on the vertices of the other faces so that this diagram could possibly make sense. Thus, we know that all of the faces are triangular, and all the numbers must be used in 2 sums. And by all the numbers being used in 2 sums, so for example, we have this vertex right here. It will be used in 2 triangles. It will also be used in the square. However, these sums do not include the square face. So it will only be used in 2 sums of which we know for this vertex. except for one exception, which is the top vertex, which will be used in all 4 sums. So the possibilities for the top vertex number are 1, 2, 4. Those are the only numbers that appear as an option in every single one of these options. Looking through the combinations, only the combination with 2 works. So for example, if we choose 1, let's say we choose this one, the first one for this one, and this one, this one. Notice that this 5 is used 3 times, invalidating this combination. And let's say we choose to look for 4s. Notice that notice that the 1 is used 3 times, invalidating this combination. But for this combination, the ones with 2s, each number other than 2 is used exactly 2 times. Knowing that the top vertex is 2, we can find the sum of all the faces, knowing how many times each vertex will appear in a sum. So remember that for each vertex will appear in 3 sums, because each sum will just be a face, so this vertex will have 3 faces, will be in 3 faces, this one will be in 3 faces, except for the top vertex, which will be in 4 faces. So we multiply 1 by 3, because the number 1 will be in 3 faces. 2 will be the top vertex, so we multiply it by 4. 3 will be in 3 faces, 4 will be in 3 faces, 5 will be in 3 faces. So then we can add all of them together. I just did 15 times 3, because the sum of the numbers 1 through 5 is 15. And then there are 3 such sums, plus 2, because there's an extra 2 for being the top vertex. That sum is 47. So then we can subtract the known sums to get the missing sum. Because the sums of all 5 faces, must be equal to 47. So we subtract the 4 faces that we know, 7, 8, 9, and 10, to get 13 for the final face, which is C. So now we're on question 26. So first we consider how to strategically paint the faces to maximize the number of one painted face small cubes. So we want to minimize the number of touching edges between painted faces, because each touching edge will paint a cube, will paint this row of cubes, which already has a painted face, with another painted face, making it so that they're no longer cubes with only one face painted. So the best way to do this is so that there are only 2 touching edges, as shown on the right. So there are really only 2 possible ways to paint a cube. The other one being that instead of painting this bottom face, which isn't shown, we paint this face on the side. However, if we were to do this combination instead, we would have 3 touching edges, one here, and one here. And that's obviously very undesirable, because we want to minimize the number of touching edges. The side length of each edge is the cube root of 64, which is 4. Because there are 64 cubes, so there are 4 cubes on each edge. Each face has 16 cubes, because we can do 4 squared. And painting 3 faces will paint 48 cubes, minus 4 cubes on each edge, which are double counted. So in case you aren't sure what that means, so keep in mind that these cubes, so we have cubes here, right? We have 4. So when we paint these over, we're really painting the same cube. So we're painting 16 unique cubes on this face. But when we go back to this face, we're only painting 12 unique cubes, because these 4 cubes will have already been painted once. So we will paint 48 cubes minus 4 cubes on each edge, which are double painted or double counted. Since there are 2 touching edges, there are 48 minus 8, which is equal to 40 cubes painted. However, the cubes on the touching edges will have 2 of their faces painted. So then we have to subtract them again to completely remove them from the cubes that we have painted. So once again, we have to subtract 8 from our sum of 40. So our final answer will be 32. We're now on question 27. So first, let x be the number in one of the empty squares in a row or column which already has 3 filled in squares. In this case, I'll use the second square of the first row, which is where I put x in the grid. So now we can start filling in the grid. Notice that the sum of each row and column must be 10 plus x for our case. If you choose a different row or column to place your x, it may be different. So the 10x is gotten by adding together all of the elements of this row. Right here, that's 10 plus x. So from here, we can continue filling it in, knowing that the sum of each row must be 10 plus x. So here we have x minus 2, because if we have x minus 2, then the sum of this row will be 10 minus x. So now we can also fill in this row, because we know that if x must be this square must be x minus 5 in order for the sum of this column to be 10 minus x. 10 plus x. And then in order for this row to be equal to 10 plus x, we know that this square must be 4. 4 plus 7 is 11. 11 plus x minus 5 is x plus 6. Plus 4 is x plus 10. So finally we have this final column in which we can get the black square. 7 is the value that will satisfy this column, so that its sum will be 10 plus x. So we get 7 for the shaded square C. Now we're on problem 28. To find the total number of games played, we add the number of times each girl played and divide by 2, since each game has 2 players. So there are 10 plus 15 plus 17, which is total number of games each girl played, divided by 2. That's 21 total games played. So looking at Alice, we can see that she rested 11 times and played 10 times. So that means that for every game she plays, she must rest. And she starts off resting, which is the only way in which she can rest more times than she plays. This creates a pattern for her. Rest, lose, rest, lose, rest, lose. So because of this, we can see that Alice must lose the second game in order for her to rest 11 times and play 10 times. If she wins at any point, that means that she'll have played at least as many times as she rested. And if she doesn't start off resting, that means that she'll also have played at least as many times as she has rested. So that just means that on the second game, she must be resting the first game and lose the second game. Now we are on problem 29. So first we draw a diagram of the problem, but with a full circle, and we reflect the peaks over the diameter. Notice that the bottom right corner of the second peak, marked O. So by the second peak, I mean this peak right here, just to clarify. And then this is the center of the circle. So let the top of the second peak be called C, and the bottom of the first reflected peak be called D. In this case, the first reflected peak would be this peak right here. And then the top of that peak, or the bottom of that peak, it'd be more of a valley than a peak, but the bottom of it would be D. So each peak and the diameter form a triangle. So for example, we have this triangle right here with the first peak and the diameter. 2 of the angles are alpha, and the third missing angle is 180 minus 2 alpha. So in this case, I've labeled the third missing angle for this triangle at the bottom right here. So the arc measure of, this is a geometry theorem, The arc measure of an arc subtended by an inscribed angle is twice the measure of the angle. So just to make sure the wording isn't too confusing, it's this theorem. This is an inscribed angle. So let's say this angle is 60 degrees. That means that the arc measure is 120 degrees. The arc measure of an arc subtended by an angle with the vertex at the center of the circle has the same measure of the angle. So an angle with the vertex center at the circle will just be an angle like this, where this is the vertex right here. And then this will be the arc that is subtended. Thus, the measure of arc AC will be equal to 2 times the measure of angle ADC, because ADC is an inscribed angle. An inscribed angle is just an angle with its vertex on the circumference of the circle that intersects the circle at 2 points not on the vertex. Then, plugging in the values for the angles, we also have that the measure of arc AC is equal to measure of angle COA, because that is an angle with the center at circle O that subtends arc AC. So then, plugging in the values for the angles, we know this is ADC is 180 minus 2A. AOC, or COA, is equal to alpha. So we have this equation. Then we can just solve for A. A is equal to 72, which is B. So finally, we have question 30. Let the smallest integer of the 8 consecutive integers be x, y, z, where each letter represents digits. We are not multiplying x, y, z together for this case. And let a, b, c represent the general form of any integer. Z is most likely 1, since the only other option is 2, which is much more restrictive than starting with 1, because all numbers are divisible by 1, and starting with 2 introduces the extra digit of 9, which is not present when starting by 1. So then we also have to worry about getting a number divisible by 9, and such a list of 8 consecutive integers may not exist. So having any other number other than 1 or 2 means that there will eventually be a 3 digits integer with last digit 0. And no number is divisible by 0. So let's say we start with 3. We have first number ends with 3, second number ends with 4. But by the time we get to the 8 number, it'll end with 0 because it'll go from 9. So let's just say we start with 123. The 7th number will be 129, and the 8th number will be 130. But 130 is not divisible by 0. So for c equals 1, c equals 2, and c equals 5, so remember, we're just saying any 3-digit integer in general. All such integers with those c's will be divisible by c because of the divisibility rules regarding those integers. For c equals 3, a plus b must be divisible by 3. In order for any number to be divisible by 3, the sum of its digits must be divisible by 3. For c equals 4, b must be even, because the divisibility rule for 4 is that the last 2 digits must be divisible by 4. So the last digit will be 4, the second to last digit will be b, so 10b plus 4 must be a multiple of 4. In order for that to be true, b must be even. For c equal to 6, a plus b must be divisible by 3, because in order for a number to be divisible by 6, it has to be divisible by both 3 and 2. If c is equal to 6, the number will always be divisible by 2, so we only need to worry about the number being divisible by 3. For c equals 7, there are multiple divisibility rules for 7. Some of them aren't as clear as others, but in this case, the one I use is that if, so let's say we have the number 147. If we were to check whether or not it's divisible by 7, what we could do is we just take away the last integer. So then we have 14. Then we subtract 2 times the last integer, which is 2 times 7. And then that would be equal to 0. So yes, 147 is divisible by 7. And if we were to do it for a different number, which might be a better example, like 161, we could do 16 minus 1 times 2. So we just find the number if we were to take away the last digit, then subtract 2 of the last digit from that number. We got 14. That is indeed divisible by 7. So in a general form, if we have the number a, b, c, but c is equal to 7, so we actually have a, b, 7. The general form of that would be 10a plus b minus 14, because it's 2 times 7, must be divisible by 7. So that's the divisibility rule I'm using in this case. If you have another divisibility rule that you like to use more, then it would probably work as well. For c equals to 8, 100a plus 10b must be a multiple of 8. Because for 8, the last 3 digits must be divisible by 8 in order for it to work. So bringing all of the rules together, we have b must be equal to 0, 2, 4, 6, or 8 from the from the rule. We have b must be equal to 0, 2, 4, 6, or 8. A plus b must be divisible by 3 from the c equals 3 rule. The first rule, b must be even, is from the c equals 4 rule. And then 10a plus b minus 14 must be divisible by 7 from the c equals 7 rule. And 100a plus 10b must be a multiple of 8 from the c equals to 8 rule. So the 100a plus 10b must be a multiple of 8 is equivalent to 10a plus b must be a multiple of 4. Because what we can do is we can see that 10a plus b, and then we can factor out a 10 from this. So this is 100a plus 10b must be equal to 0 mod 8. Modulus just means the remainder for division by 8. So essentially, this is 10 is 2 times 5. In order for this to be a multiple of 8, 10a plus b must be a multiple of 4. So let's just say we have 4 times n, then that creates 8n times 5. So we just need 10a plus b to be a multiple of 4. These will be multiplied by 2 anyways by the 10. So in this case, b must be even, because in order for 10a plus b to be a multiple of 4, it must also be divisible by 2, so we also have the divisibility by 2 rules. So now we consider all possible values of b, and b must be even. So we first consider b equal to 0. We look for values of a satisfying the other conditions. So first condition is a plus b must be divisible by 3. We have 3, 6, 9. Then we have 10a plus b minus 14 must be divisible by 7. For that, the only possible value is a equals to 7. So before we even consider this last divisible by 8 condition, we can already realize that b cannot be equal to 0 because we already have a contradiction here. So now we move on to b equal to 2. We go through the same process, but this time at the last condition, 100a plus 10a plus b must be a multiple of 4. We see that there's no possible a that would work. Now we move on to b equal to 4. In this case, we see that for all of the statements, there's one value of a which is present in all of them, which is a equal to 8. So to confirm our answer, we have the integers. Is remember A represents the hundredths digit, B represents the tenths digit, and C represents the units digit. So you have the integers 841, 842, 843, 844, and then all the way up to 848. If you were to check for them, they are indeed all divisible by their last digits. So the smallest of them is 841, which is equal to, the sum of its digits is equal to 13. So this is the end of the Math Kangaroo test. Hopefully you have learned something along the way of this solutions video. And thank you for watching.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!